going into the AC analysis. In the AC analysis, of course, VS is there, which is basically the output of the previous stage, if we consider a cascaded case. Then we have RS. As we enter the transistor, we get input impedance observed from that input point. Once more, we can go with T model. So we'll get to the collector current IC flowing there. As we go to the collector, we go straight to ground because, well, the collector is directly connected to ground, and that will be the collector side. That will be IC, which is GMV pi or beta IB. And as we go to the emitter side, we go through RE, we reach the emitter. As we reach the emitter, we've got RL, and then we go to ground. So the input is on the base, the output is on the emitter. So in terms of the output on the emitter, it's observed by looking into the emitter as follows. That will be R out. Okay, so in terms of R in this case, that will be the resistances observed from that point looking into the input of the transistor, and that is nothing but RE. RE. When it comes to it's not RE. Actually, looking into the base, you won't see RE. Let's be careful. Looking into the base, you will normally see R pi. Very important, because the resistance you see is caused by V pi looking into the base. The difference between common base and this one is that here we're looking through the base, so it's actually R pi. But you're also gonna see beta plus 1 RL as you look all the way from the input to ground. So a typical way of drawing this is the T model, but if one was it would be more convenient to draw it in terms of the hybrid pi model. Then you go from the base. It will be much easier to see it using the R pi model. As you get to the emitter, you get RL all the way to ground. So VI will be there. So we've got IB flowing there, we've got IE flowing here. That is, you can see it's R pi plus RL times beta plus 1. Okay, that will be basically the input impedance considering the load, so with the load included. But normally, since we calculate R in without the load in general, so if you ignore RL, so R in is just R pi. At the same time, R out, which is the resistance now looking into the emitter, and that way the T model becomes much more interesting, because when you look into the emitter, R out is nothing but RE. It's only RE you see. Okay, so the T model allows us to easily see R out. The R pi model, hybrid pi model, easily shows us R in. Right. So each of the two models, when it comes to the common collector, has its advantage. None of them takes precedence. But one must just be analytical and critical. So this would have been R in loaded. So I don't want you to use that. We just use a non-loaded R in. So then we take into account the loading effect after. Okay. So the gain, in terms of the gain, the input the unloaded gain, of course, which is V out over VI. VI is still R pi IB, which is the unloaded gain, unloaded without considering RL basically, and V out is still is the voltages measured from the output, which is on the emitter, so that's the V out point, from there to ground, and from there to ground, without considering RL, you would get RE IE, because IE is the current flowing there. So now IB is flowing this way, IE is flowing this, they're flowing in the same direction, so that justifies the fact that the gain is positive. So knowing that RE is R pi over beta plus 1, at the same time IE is beta plus 1 IB, if you divide that by R pi IB, you get that cancel, and you get R pi to cancel, you get 1. So this is very important. The unloaded gain or open loop gain of a common collector amplifier is 1. That's why we refer to it as the emitter follower. Emitter follower, meaning since the input is applied at the base and the output is taken on the emitter because it's common collector, then it's more like the emitter is just following what's happening at the base, and since the gain is 1 as well, of course. So as the signal on the base goes high, which is the input, the signal on the output also goes high, because by the same magnitude. So the emitter is just following the base. That's why we call it emitter follower. Emitter follower is not common emitter. Emitter follower is common collector. Okay. But why would you need an amplifier with a gain of 1? That has been answered already. I think this is the aim of designing this common collector amplifier is to tap into its guaranteed low output impedance, which is a good characteristic of an amplifier. That's why as different modes are being cascaded together to form a good amplifier design, I mean more or less ideal, you normally put the common collector mode at the end in order to tap into its very low output impedance. You're not really after gain out of it, because it has got no gain. It has got a gain of 1 when unloaded, as we proved it just now. So what is the common collector fully loaded gain? GV or AV fully loaded. Meaning now you're considering RL and RS. So if one considers RL and RS, first of all, the impact of RL, which is V out of a VS, of course. The impact of RL will come, of RS, will come in. Okay, we can work out VI, which is VS times R in over R in plus RS. But now here you must be careful, because now we're considering RL. So R in now considered here is the loaded version, which means we are in the case where we consider R pi but also RL all the way to ground. So the R in we're considering here is actually R pi plus beta plus 1 RL. Must be careful with that, because we are in a fully loaded case. That's R in loaded, meaning we also R in that considers the presence of RL. So that would mean that VS is, which is VI times RS plus R in over R in, will become VI RS plus R pi plus beta plus 1 RL, all of that divided by R pi plus beta plus 1 RL, which is R in loaded now, plus RS. So if we were to take that into here, this value of VS basically, then we would get GV to be V out over VI times, well, we know that this is R in loaded, to be specific, this guy, because in this case we've got R in loaded and unloaded. This is R in loaded divided by R in loaded still plus RS, because that's that parameter there showing, and if you go, that will be the unloaded gain times R in loaded plus RS over R in loaded. So that's still the input loading factor, with the only difference that here it's R in loaded. This is because RL forms part of R in this time. Okay, so then when we consider RL, we must then take it into account. At the same time, we also have to consider the impact of RL on the output. So RL influences the input as well as the output. So because now this is V out with RL, it's no longer the V out we considered before. Sorry. So that will be, V out with RL over V in. So V out with RL being considered is basically captured by the output loading factor, which is RL over RL plus R out. But now this is R out without RL, which is just RE. So RL plus RE. So to get a fully loaded gain, then you take the output loading factor, you multiply by the input loading factor, but with R in loaded, of course, as we discussed, times the open loop gain, which is happens to be 1. So we can ignore it. So that ends up becoming simply RL over RL plus RE, all of it multiplied by R in, all of it multiplied by R in, VS equals to that. All of that multiplied by R in loaded, R in loaded, basically, because VS is VI times RS plus Rn over Rn. Okay, so that made if we substitute that in there, Rn will go on top. So yeah, that will be R in alone, on top, divided by the sum underneath. Yeah, so that will be Rn loaded over Rn loaded this time plus Rs, which is the input loading factor with Rn loaded, meaning Rn in which there is RL. And if one carries this further, you get GV, which is the fully loaded gain, to be RL over RL plus RE, which is R out. The R in loaded we're considering here is R pi plus beta plus 1 RL divided by R pi plus beta plus 1 RL, which is the R in loaded, plus all of it plus RS. So now, with the assumption that RL could be very much bigger than RE, the component RL over RL plus RE tend to be almost equal to RL over RL, would tend to be equal to 1. So yes, we are below 1 basically, because that component will always be less than 1. But close enough to 1, about 0.99 most of times. The same applies to the second part, which is also this component in the assumption that R in loaded is very much bigger than RS, then that will also approximate 1. So the fully loaded gain of a common collector amplifier is also almost 1. But slightly lower than 1. So by having a common collector, the trade here is to lose a bit of gain, because now it becomes an attenuation. If a gain is below 1, then that's an attenuation. So it's a way to lose a bit of gain, but at the same time achieve low output impedance, which is very important for characteristic of an ideal amplifier.